Hi, my name is Ryan Johnson. I'm a PhD student in electrical and computer engineering at the University of California, Santa Cruz. My educational background includes bachelor's and master's of science degrees in aerospace engineering from the University of California, Los Angeles. My research at UCSC in the Hybrid Systems Lab under Professor Riccardo Sanfelice focuses on the analysis of what are called hybrid dynamical systems. These are systems that exhibit both continuous time dynamics, called flows, and discrete time dynamics, called jumps. A canonical example of a hybrid system is a bouncing ball. As the ball travels through the air, its position and velocity change continuously with time, as shown in Figure 1. However, each time the ball impacts the ground, the direction of its velocity vector changes instantaneously, signifying a jump. Other examples of hybrid systems include analog to digital signal converters and electrical circuits with switches. Advances in the field of hybrid systems have wide-ranging applications in power systems, robotics, and aerospace. I'm interested in the topic of parameter estimation and system identification for hybrid systems, also known as hybrid learning. For example, in the bouncing ball problem, we may be interested in determining the mass or the elasticity of the ball based on measurements of the ball's position and velocity. My recent research focuses on developing hybrid gradient descent algorithms for parameter estimation of hybrid systems. Gradient descent methods seek to determine a local minimum of a function by taking repeated steps in the direction of steepest descent. We applied these methods to an electrical circuit called a DC to DC boost converter, which is a common component in the power systems of electric vehicles. The boost converter, shown in Figure 2, consists of a voltage source, an inductor, a capacitor, and a switch in connection with an output load. The purpose of the circuit is to provide a higher voltage at the output compared to the input by toggling the switch in a particular manner. We developed a hybrid gradient descent scheme which estimates the input voltage and load resistance of the circuit in finite time. Furthermore, we designed an adaptive uniting control algorithm which uses a globally stabilizing control scheme that's applied during transients in combination with an industry-standard pulse width modulation scheme that's applied locally near the set point. All of these elements are shown in Figure 3. On the left, we have the uniting control scheme with trajectories under the global controller shown in blue and trajectories under the local controller shown in magenta. On the right, we have the estimates of the input voltage and load resistance, each of which converge to the true values in finite time. We provide formal proofs that guarantee global asymptotic stability of a neighborhood of a desired set point for the closed-loop control algorithm, even under uncertainty in the input voltage and load resistance. Thank you all for your time, and thank you to the ARCS Foundation for helping to support me and this research.